Hello, everyone. We're going to jump into the first week of your course in dynamic balancing. I'm going to start off and just give a brief kind of introduction to dynamic balancing, what it's all about, what unbalance is, how it's measured, and some of the effects of it. And we'll kind of work through. By the end of this course, you'll be using computers and balancing equipment to actually balance rotating equipment to decrease the load on the bearings and on machine parts and components. So yeah, we'll just start off with just some of the basics of dynamic balancing. So unbalance of rotating machine components remains as one of the leading causes of vibration. So this really ties in very closely to the vibration analysis course. They kind of go hand in hand. Simply, there's just so many different ways unbalance can occur, and correcting imbalance is a very simple task. And once you understand a few of the basic principles, it's quite easy to do, and it's quite easy to see that connection with the vibration analysis and how, because it is the most common source of vibration, the reduction in it and the monitoring of your vibration in your preventative maintenance program or your predictive maintenance program all kind of go hand in hand together. Most present day vibration and analyzers and even data collectors have the means of providing the necessary data, vibration, amplitude, phase, whatever needed to solve most balancing problems. Some instruments actually incorporate balancing programs that automatically calculate the needed balance corrections. The operator needs to do all the operator needs to do is follow like a simple menu of instructions. You come in, and put the accelerometer on. It tells you to turn it on. It takes a reading. You put on a trial weight, and it kind of walks you through. If you've ever worked with a laser alignment tool, it's a similar type of process. Measure what are the distance between the feet. What is the diameter of the coupling? What is this? What is that? You enter in the information, and then it tells you, kind of walks you through the same type of thing with some of the newer balancing equipment that you're going to see. So once an imbalanced condition has been diagnosed through analysis, I can possibly actually it may be possible to actually balance the machine in place, eliminating the costly time consuming disassembly. All that's required is that the unbalanced component be accessible for the addition and removal of balance correction weights, which is all stuff that we're going to talk about. But you don't have to necessarily disassemble a rotating piece of equipment and the shaft and take it to a shop and put it on a balancer. You can do it in place, and it can save you a lot of time, and it's very realistic to do. So I'm going to introduce you to the basic principles of balancing, along with recommending procedures for tackling single plane and two plane balancing problems. I'm not going to make an attempt to cover complex balancing problems such as multi-plane balancing, flexible rotors on like paper machine rolls or multi-stage turbines and compressors and that kind of thing. That's kind of outside the scope of what we're going to do. We're going to stick with the kind of the basic dynamic balancing. So unbalanced defined. Unbalanced is often defined as simply the unequal distribution of weight of a rotor around its rotating center line. Or according to the ISO, or International Standards Organization, the condition which exists in a rotor when vibratory force or motion is imparted to its bearings as a result of centrifugal forces. So there's a lot of mouthful there in your Alberta book. You're going to be able to read the definitions and kind of wrap your own head around it. But all shafts have a axis, and if all of the weight is distributed perfectly evenly around that axis as it rotates, there's no centrifugal force that's going to be shot outwards. And if it's balanced around the axis as it's rotating and there's no radial load being thrown out, there's less impact and load being placed on the bearings, and therefore the bearings will last longer. Okay, so regardless of the definition, however you want to define it, whether it's the ISO or what's in your Alberta book, excessive balance results in vibration of the rotor and supporting bearings, and unbalance creates forces that are detrimental to the life of the machine and its components, parts, etc. The rotor bearings and supporting structure all have to take that load, so the less vibration or less imbalance that we have, the longer the machine will last. Another important reason for balancing a rotor is that unwanted vibration from unbalance can cause poor product quality, especially in the case of machine tools, grinders, that kind of thing. A slight imbalance in a precision grinder, for example, can produce chatter marks or waviness in the finished workpiece. In addition, studies show that even small amounts of imbalance can accelerate the wear on cutting tools and grinding wheels. So if you're working around machine shop or in the manufacturing process, with any type of machine tool, these are all things that need to be taken into account. Unbalance results in vibration, which can be measured in units of vibration displacement, velocity, or acceleration. Okay, so that's going to be stuff that we're going to cover in the vibration analysis course. However, the actual units of imbalance that we're going to cover in this course are slightly different. They're expressed as a product of an unbalanced weight, ounces, grams, etc., times its radius or its distance from the shaft center line, inches, centimeters, etc. So, for example, this diagram here, figure, shows a weight of 8 ounces at the top here, and that 8 ounces is located at a radius of 10 inches. The amount of this imbalance would be expressed as 80 ounce inches. Okay, so 8 ounces, 10 inches from the center. Similarly, the weight of 6 grams at the radius of 20 centimeters would be an imbalance of 120 gram inches. Okay, so the one at the bottom. So it is a different unit of measurement that we can do it, whether it's imperial, ounce, inches, or it could be gram, centimeters. Of course, vibration analyzers and data collectors, which can be used to solve these balancing problems, do not actually measure imbalance in units of ounce inches, gram inches, or other imbalance units. These instruments measure unbalance amplitude in units of displacement, velocity, acceleration, stuff we're going to cover in the vibration analysis course. Okay. However, it is acceptable because the amount of imbalance is directly proportional to the amount of unbalanced vibration. So, for example, if the unbalance of a 10 ounce inch was added to a perfectly balanced rotor and caused 10 mils peak to peak vibration displacement, an unbalance of 20 ounce inches would cause 20 mils of vibration displacement. So, in other words, there's a linear relationship between the amount of rotor imbalance and the resultant amount of unbalanced vibration. So even though a portable balancing instrument does not actually measure units of imbalance, the vibration amplitude is proportional to unbalance and can be used to represent the amount of unbalance. So it's not measuring how many ounce inches, it's measuring the amplitude. But by measuring that, you can do a relationship because it's directly proportional to these units, and that's how the portable vibration units operate. So in the beginning of a balancing problem, the relationship between the units of imbalance and the units of vibration amplitude is not known. We don't know. We have to figure out this relationship. How this relationship is determined is to find the amount and location of balance correction required will be discussed later in this course. So we'll cover that later. How do we find out this relationship between our vibration sensor and the actual units of imbalance so that we can make those corrections on our balancing. So when you're balancing a machine in place, the normal practice is to measure the unbalanced vibration amplitude in units of displacement. So that's mils or microns or something that we're going to cover in vibration. Vibration velocity or even vibration acceleration units could be used. However, machines operating below 20,000 RPM, displacement simply provides a larger number to work with. So we're actually measuring the displacement or the shaking. Okay. So it was mentioned already that the importance of balancing rotating equipment components is due to the destructive forces and vibration caused by imbalance. The amount of force generated by an unbalance is not only depends on the amount of imbalance, like how many ounce inches or gram inches or whatever, but the rotating speed as well. So the actual equation that can be used to calculate the force by an imbalance is here in this slide. The actual equations are quite straightforward and simple. All that is needed is the unbalanced weight, the radius of the unbalanced weight, and then the rotating speed. Okay, so from this calculation, there's a lot of, you can go through and you can calculate all of this out, but the F is your force, so in pounds or in kilograms or whatever the unit. Okay, but the reason why I'm putting this slide up here is it's really important to realize that the force due to unbalance is proportional to the square of the RPM. Okay, so I'll repeat that. The force due to unbalance, so the amount of force that's actually being, pushed through the bearings, additional to the weight of the shaft, okay, is proportional to the square of the RPM. Okay, so doubling the RPM of the machine actually increases the imbalance force by a factor of 4 times. So to illustrate, assume that the rotor operating at 3600 RPM has an imbalance weight of 3 ounces at 30 inches. Okay, so we could plug those numbers into our formula. I'm not going to do that for you. There'll be some examples in the book that we'll cover later. But the actual force generated by this imbalance is about 2,000 pounds. But by doubling the RPM from 3600 RPM to 7200 RPM, the imbalance force would increase to nearly 8,000 pounds. So clearly, a very small imbalance weight can sometimes produce tremendous and often destructive forces on the machine and in the equipment. So that's why this balancing is so important. And the higher the speed of the rotating shaft or whatever it is that you're balancing, fan blades, impellers, the higher the speed, the more critical the balancing becomes, because that rotational speed can increase if every time it doubles, the amount of force that it's exerting on the bearings goes up by 4. Okay, so this is really, really critical. So how do we get imbalance? One of the reasons imbalance remains as one of the leading causes of machine vibration is because there's so many possible causes or sources. So we have a list here, and I'm going to kind of go through and discuss some of the more common causes of imbalance. Casting imperfections. So casting rotors such as pump impellers or large pulleys will occasionally have blowholes or sand traps, which would result in the casting process. Such defects may be present within the material or and undetectable by normal visual inspection. Nevertheless, the void created can cause a significant amount of imbalance. So when they pour and create castings, there can be little pockets that you can't detect or see. Maybe it's painted. You don't get to visually be able to see it, but they could be there. So it's critical when you go to rebuild or install a pump that you would put it on the balancer and you try to, it doesn't matter how many of these little pockets there are or extra weight, but you have to eliminate the imbalance that it presents. Eccentricity exists whenever a geometric center line of a part does not coincide with its rotating center line. So the rotor itself may be perfectly round, however, eccentricity results in more rotor weight on one side of the rotating center line. So although most rotors can be balanced to compensate for the unequal distribution of rotor weight, eccentricity of some rotors may cause forces that may not be totally corrected by balancing. So an eccentric V-belt pulley, for example, might create reaction forces due to the variation in belt tension. And eccentric motor armatures will cause imbalanced magnetic forces between the armature and the stator of the motor that can't be corrected by balancing. These are just things that you just have to deal with. This really ties back to tolerances and fits, which is how tightly things fit on a shaft. and how much, like for example, a coupling. If a coupling hub is bored out oversized and then the set screw kind of pulls it off center, you're creating an eccentricity within the machine that needs to be balanced. The addition of keys and keyways is a really important one. So although the normal practice is to balance rotors with a key slot filled, so when you'll do the balancing, you actually take a piece of key stock and fit it in and mount it inside of the shaft. There's a few standards governing the use of full keys, half keys, or no key when balancing manufacturing or rebuild components. Even if the rotor was balanced at the factory repair shop with the key slot filled, once the machine is installed, unbalance may result if only a partial key is used. So the best approach is to balance the complete machine assembly using the key that's going to be used in the final installation. So you don't want to have like a dummy key and then you change that out and then you go and you change a coupling or you do something and then you make your own key. You want to actually, that's how critical some of these weights can be to the rotating equipment. Distortion, although a part may have been well balanced at the time of manufacture, there may be influences that can cause the rotor to distort or otherwise change the shape of the rotor to change the balance condition. Common causes of distortion could be stress relief, and it could be also thermal distortion. So if you're heating things up to install hubs or you know, applying heat for bearings, if you've changed a bearing on something. So these are all things that you need to rebalance. Stress relief can be a problem with rotors that have been fabricated by welding or shaping and pressing, drawing, bending, extruding, all that kind of stuff. Such rotors may have a high levels of internal stress. If the rotor is not stress relieved before balancing, some stress relief will occur naturally over a period of time. This is actually cause the rotor itself to change its shape slightly, resulting in a change of imbalance. Distortion that occurs with a change in temperature is called thermal distortion, and nearly all metals naturally will expand when heated, although machine parts may expand unevenly, and that could cause an imbalance. It's a pretty common problem on machines that operate at elevated temperatures, such as boiler draft fans, or thermal distortion may require that a rotor be balanced at normal operating temperature, even though it might have to be balanced well when it was cold as well. So if you have a machine that's going to be heating up and running at a very different temperature, sometimes you actually have to run and balance that at that high temperature to try and get it, because you won't be able to, it'll distort so much as it changes temperature that you won't be able to actually properly balance it. Clearance tolerances. One of the most common sources of imbalance is the take-up of clearance tolerances during the assembly of machine components. So if the bore diameter of a pulley, a coupling hub, a fan rotor, pump impeller is greater than the shaft diameter when a key or a set screw is used, the take-up of clearance shifts the weight of the rotor to one side of the rotating center line. And this results, of course, in imbalance. That's why it's desirable to balance the complete rotating assembly if possible, to put this machine all together and then put that on your balance, or balance it in place so that it's already all assembled the way that it's going to be. So if there is a clearance take-up, you can add or remove weight to counteract the offset from centerline. The corrosion and wear is one that's very common, especially in pumps. Many rotors use environments that are subject to abrasion, wear, corrosion, and of course imbalance will result when wear or corrosion isn't uniform. So a lot of pumps will over time have cavitation, or they'll get kind of eaten away, and that is going to obviously create an imbalance. The opposite of that is a deposit buildup. So rotors used in material handling may become imbalanced due to the unequal buildup of dirt or pulp or dust, slime, any substance that can like stick and build up over time. And although a buildup may occur gradually, a serious problem will occur when chunks of deposit begin to break away. Obviously, rotors with deposit buildup should be cleaned before balancing, but as the machine is running over time, and you do a vibration analysis on it, or you try to balance it in place, dust and debris will just start piling up, which obviously can create an imbalance. Last part here I want to talk about is something called the heavy spot. Okay, so from that above all that stuff that I just talked about, it's pretty apparent that there are many reasons a rotor could be out of balance. And in many cases, a rotor may have more than one source of imbalance. So as a result, it is impossible to simply look at a rotor and determine the actual amount of location of unbalance. But fortunately, regardless of the number of imbalance sources a rotor may have, all sources of imbalance in a given reference or balance plane will vectorially combine to produce a single heavy spot at a certain angular location on the rotor where weight can be removed or to successfully balance the rotor. Of course, if the weight cannot be removed, then you can be added on the other side to remove the light spot. So there's a heavy spot and a light spot on all rotating equipment, and we'll see that when we go to the shop. When you rotate the shaft, there's going to be a heavy spot that's going to fall to the bottom. Okay, so that's your heavy spot. You'll measure it based off of a arbitrary kind of reference point, and then we'll rotate through and calculate how heavy that spot is. And then the idea is just like a teeter-totter. Instead of a linear teeter-totter, we're talking about a rotation around an axis. So if we know where the heavy spot is on one side of the axis, we just add the same amount of proportionate weight from the center line on the other side, and then that should balance it out. Okay, but it's a little more complicated than that. I'm describing a static balancing. We're going to talk about all the different types of balance that we could see, and the next week. Okay, so for right now, these are the this is the kind of introduction to balancing. So for your weekly assignment, what I want you to do is go through the Alberta ILM on balancing, page 2 to page 6, and it talks about a lot of these different types of or causes of imbalance that I talked about. I want you to pick 3, and I want you to make a little write-up or a chart or something that kind of explains how human error, how technicians can be the cause of some of these type forms of imbalance, or how we can actually correct it, how it's maybe something that's be very easy. So I want you to kind of go through and just kind of like think back to your time, like what was something that maybe you've done or what you've seen, or what are some of the things that causes or can add to these causes of of imbalance, and hand that in. That'll be the end of week 1. So yeah, we'll see you next week. Next week we're going to cover balancing forms of imbalance. There's a few different terms, and I want to explain the difference between them, and then we'll just keep rolling on through the course.